So we have defined a brass space, and also we have used the brass space to form an inner product, right? So let's see how these things work by looking at an example. Right? So let's go back to our spin case. Right? We said that ket sz plus corresponds to a state with a definite spin value along the z direction, right? So we already said that if the state is given, so we are talking only about this two-dimensional space. So we are talking only about the spin of the electron, okay? So if the state of the electron is represented by this ket, right? So this ket is characterized by the eigenvalue for the Sz operator. We already said this. This Sz operator acting on Sz plus gives you plus h cross by 2 Sz plus. Right? So we see that if the Sz operator acts on this ket, you just get a multiple of the same ket. So we say that this ket, okay, this Sz plus is an eigenvector of Sz corresponding to the eigenvalue plus h cross by 2. All right. Now this means that any measurement of Z component. So we said that the measurement outcomes are related to the eigenvalues. So any measurement of Z components of Z component of spin on this state will always yield h cross divided by 2. Okay. So since this is an eigenstate of Sz, if you measure Sz on this state, you will always get h cross by 2. Similarly, if you are talking about this this state Sz minus, which is an eigenvector of Sz with eigenvalue minus h cross by 2. Right? So if this is the physical state, any measurement of Sz on this state will always yield minus h cross by 2. Right? So these are two possible states for the system. But in quantum mechanics, there is something called superposition. This also is a possible state of the system. Okay, it could be a superposition of Sz plus and Sz minus. It could be a superposition of Sz plus and Sz minus. All right, so we have basically combined Sz plus and Sz minus using these complex numbers to get another ket. All right, now based on our basic postulate for quantum mechanics, each ket represents a physical state. So if these two are physical states, then this also is a physical state. Okay, this also represents a physical state. Okay, so for this state, what happens to this state? If you measure Sz on this state, you will get either plus h cross by 2 or minus h cross by 2, but which we don't know which. Okay, we don't know what we'll get if you measure the z component of spin along, so in this state, we don't know what we'll get. Before the measurement, we don't know what we are going to get as a measurement result. We could either get plus h cross by 2 or minus h cross by 2. What quantum mechanics predicts is the probability for getting h cross by 2 or minus h cross by 2. Alright, so this is a superposition of two eigenkets of Sz operator. So we are talking actually about a space spanned by the eigenkets of Sz. Okay, let's get familiar with this language. We are talking about a space spanned by eigenkets of Sz operator. Right? Measurement of Z component of spin on this state yields plus or minus h cross by 2. We don't know which. Okay. The vector space here is the span of the vectors Sz plus and Sz minus. Right. Now Sz plus and Sz minus are base vectors that span the space. That's another way of saying the same thing. Same thing. We can say that Sz plus and Sz minus are base vectors that span the space. Okay, which means that any possible state can be written as a linear combination or a linear superposition of these two base vectors. All right, or any physical state in this space can be decomposed into two vectors. All right, one vector proportional to this one and another vector proportional to this one. All right. Now, measurement of Z component of spin on this state is plus or minus h cross by 2. Quantum mechanics, what quantum mechanics does is to predict the probabilities for obtaining either value. Right? So, quantum mechanics predicts the probabilities for obtaining either value. So, one ingredient to quantum mechanics that we did not state earlier. Right? So, we have not discussed this yet, but I'll just state it here. We'll be seeing these things in more detail later on. All right. So how do we calculate these probabilities? Okay, how does quantum mechanics predict these probabilities? Okay, the rule is quite simple, right? Even though we don't know why this works, the rule is simple, right? You could call it the Born rule. named after Max Born. All right, you could call it the Born rule. The rule is quite simple. The probability for measuring plus h cross by 2 is proportional to modulus of C1 square, and the probability for measuring minus h cross by 2 is proportional to modulus of C2 square. So let's look at the state again. If you are measuring, the postulate says that if you are measuring the spin, the z component of spin in this state, you will get the two possibilities, plus h cross by 2 and minus h cross by 2. The probability for getting plus h cross by 2 is proportional to modulus C1 square, right? The modulus square of the expansion coefficient that appears here, right? Also, the probability for measuring minus h cross by 2 is the modulus square of this expansion coefficient, right? This is the Born rule, or this is how we calculate probabilities. All right. These are the expansion coefficients when alpha, ket alpha, is written in terms of the eigenkets of Sz operator. The dual correspondence for these base vectors, all right? So these are the base vectors Sz plus and Sz minus. Okay. Again, we talked about a dual correspondence. The dual correspondence for these base vectors can be written as corresponding to Sz minus, corresponding to ket Sz minus. There's a bra Sz minus. Okay, and corresponding to a bra Sz minus, there's a ket Sz minus. Okay, similarly, corresponding to ket Sz plus, you have got a bra Sz plus, and this we can talk about an orthogonality relation. Okay, Sz plus, bracket of Sz plus with Sz minus is 0. Okay, this we actually know from the physical motivation. Right, if you have a state characterized by Sz plus, okay, and if you send it to an SGZ hat apparatus, all right, you get only one output. You get only what is electrons characterized by Sz plus, all right. There's no beams characterized by Sz minus, all right. There's no beams with minus h cross by 2. Okay, this means that Sz plus has no component along the direction Sz minus. Okay, so we can say that Sz plus, based on this experiment, we can postulate that ket Sz plus has no component along the direction Sz minus, if you like. All right, or we can say that the scalar, we can say these are orthogonal to each other, or the scalar product or the inner product, sorry, I should use inner product. The inner product of Sz plus with Sz minus is 0. This is basically orthogonality. Okay, this means that Sz plus has no component in the direction Sz minus. Okay, now physically, in our case, this means that if you are measuring this Sz component, right, so sorry, if you are measuring the Z component of spin in this state, you will never get minus h cross by 2. You will never get minus h cross by 2. But if you are measuring an x component of spin along this direction, you could get plus h cross by 2 or minus h cross by 2. Okay, this means that, all right, let's not go into so much detail. So this just means that Sz plus has no component in the direction Sz minus. Okay, now, so we can say that these are orthogonal states. Okay, these are orthogonal states. Now we can choose base vectors that are normalized to 1. We always use unit vectors for base vectors, right? Even in Euclidean space, we always have x hat dot x hat equal to 1, y dot y is equal to 1, z dot z equal to 1, or we might call them as ijk. We use unit vectors. In the same way, it's better, okay, it's easier to use base vectors which are normalized. Again, we had the normalization condition earlier. We can always choose the base vectors in such a way that they are normalized to 1, which means that the inner product with itself is equal to 1. The inner product with itself is equal to 1. All right. Now let's look at the state ket alpha. Let's talk a little bit about the state ket alpha. All right. Now we had ket alpha like that. Ket alpha is equal to C1 Sz plus C2 Sz minus, right? Okay. Now using orthogonality, all right, we could find this scalar product, sorry, this inner product Sz plus bra Sz plus ket alpha. We could find this inner product. Okay. we get something like this. So since it doesn't matter where we put this number, we can write this as C1. All right, I'm just pushing a bra SZ plus from the left. Okay, I'm just pushing a bra SZ plus from the left. All right, so since this is a number, I can simply take it to this side, and then this becomes SZ plus SZ plus, okay, plus C2 SZ plus SZ minus. All right, now by orthogonality, this is 0, because from the experimental side we already saw that SZ plus has no component along SZ minus direction. So these are orthogonal states. So this is 0. And we had already used normalized base vector. So this is equal to 1. So we see that the bracket SZ plus alpha is equal to C1. Okay, what does this mean? This is the projection. We could think of this as the component of alpha along the SZ plus direction. Right? You could think of this as C1 as the component of alpha along the SZ plus direction. Right? Similarly, you could find the component of alpha along the SZ minus direction. That will be written as C2. That will be obtained as C2. All right. Now this is very similar to the thing. Let's talk about these vectors, usual Euclidean vectors, axx plus ayy plus azz. Right. Now from this vector we could actually find the component of a vector along the x direction. What you do is just take the scalar product, or you project a vector along the x direction, or you take the scalar product, you take the inner product between x hat and a vector. That will give you ax. Okay, what is ax? It's a component of a vector along x hat direction. Right. In the same way, c1 here is the component of ket alpha along the sz plus direction. Okay, so the logic is the same. Now, writing c1 as bracket of sz plus alpha and c2 as bracket of sz minus alpha, we can write the ket state alpha. Okay, we can write ket alpha as this is simply c1 sz plus c2 sz minus. Right, so we have got ket alpha is equal to sz plus ket alpha, or bracket sz plus alpha. So this is c1. So this is c1 sz plus c2 sz minus. So we have rewritten the same expression here that appeared here. All right, the same expression we have rewritten in this form. Right? Now let bra alpha be the dual vector of bra, or bra corresponding to ket alpha. So we said that there's a dual correspondence. So let's say that bra alpha is the dual vector, or bra corresponding to ket alpha. Okay. Now since to every ket there is a bra, so what have we done here? We have expanded ket alpha in terms of the eigenkets sz plus and sz minus. All right. Now in the same way, we can write bra alpha in terms of the corresponding eigen bras. Okay, because there's a dual correspondence. Corresponding to ket alpha, there's bra alpha. Corresponding to this ket sz plus, there's a bra sz plus, and corresponding to this ket sz minus, there's a bra sz minus. Okay, but this expansion coefficients, I'll simply write it as C3 and C4, because C1 and C2 we have already used before. So we don't assume anything yet about the C3 and C4. So I am writing simply bra alpha. Okay, I'm writing bra alpha as a linear combination of these eigen bras. All right, here I am writing ket alpha, or here I am writing ket alpha as a linear combination of the eigen kets. Here I am writing bra alpha as a linear combination of eigen bras. Okay. Now C3 and C4 are expansion coefficients which can be found using orthogonality relations. Again, we can use orthogonality relations. All right. So here what we have is bra alpha. Okay. What happens if I push a ket sz plus from the right? What happens if I push a ket sz plus from the right? I'll get C3 sz plus okay, plus C4 sz minus sz plus. I have simply pushed an sz plus, a ket sz plus from the right. Okay, what do I get here? This is 1 because we had already used normalized vectors, base vectors. This is equal to 0 because of orthogonality. Okay, so I get C3 is equal to bracket alpha sz plus, and similarly C4 is bracket alpha sz minus. All right. Now again with this we can write bra alpha is equal to This is C3 and this is C4. Instead of C3 and C4, I have just used these expressions. That's all. Okay. Now, since ket alpha and any scalar multiple of it represent the same state, we may demand that bracket of alpha with alpha equal to 1. Okay. So we assume that alpha is normalized. Assume that alpha is normalized. If it was not normalized, we could simply normalize it by dividing it by an appropriate number. Okay. So let's say that this state alpha is also normalized. Okay, that is, we can choose to represent unit vectors in the complex vector space to represent quantum mechanical states. Okay, so we'll be using unit vectors in the complex vector space to represent quantum mechanical states. Why do we do this? One thing is convenience, and the other thing I'll discuss immediately. Because if alpha is a state, C alpha is also a state. So C alpha also represents the same state, same physical state. Right? So we might as well use unit vectors instead of vector of any length. We could use unit vectors to represent states. Okay, that's what we are doing here. We are demanding that bracket of alpha with itself is equal to 1. Right? So we are choosing the state vector such that it is normalized. We are using normalized states here. All right. Now, this requirement is crucial for the probabilistic interpretation of quantum mechanics. So, I have been saying this many times, probabilistic interpretation of quantum mechanics. Let's see what it means in this example. Okay. All right. First, let's examine the inner product of alpha with itself, bracket alpha alpha. All right. So, bracket alpha alpha, we already had ket alpha is equal to, we had sz plus alpha, sz plus sz minus alpha, sz minus, right? This we already had. Similarly, we had bra alpha in the same form, right? So bra alpha was bra alpha sz. This was actually C3. So this is bracket alpha sz plus. This means the component of bra alpha in the direction sz plus. Okay, or the other way about. Doesn't matter in which way you say this, all right? So here I am expanding bra alpha in terms of the eigen bras sz plus and sz minus. These are the expansion coefficients which we previously denoted as C3 and C4. Okay, here I have got this ket alpha, which is written as a linear combination of sz plus and sz minus, ket sz plus and ket sz minus, and these are the expansion coefficients which we previously denoted as C1 and C2. Okay, C1 is the component of alpha along sz plus, and C2 is the component of alpha along sz minus. All right. Now we combine these two. We are taking the inner product, so we take the inner product of each term. So let's do this. First term, you combine this thing, right? This with this. Right. Now these are numbers. We separate out the numbers. This is the number. What do you say? C3. Yeah, was it C3? Yeah, that's C3. And this is basically C1, right? Yeah, this is C1. Okay, so these numbers I write first. I multiply the numbers together and write here. This is basically C3 multiplied by C1, and then I have to combine this bra and ket. We know how to combine the bra and ket. We combine it into a bracket. So this becomes bra sz plus ket sz plus. Okay, this is bra sz plus ket sz plus. So combining these two terms, okay, we are multiplying these two expressions, bra alpha to ket alpha. This is how we do this multiplication. All right, you just combine these terms. So you combine this bra with this ket and you get the corresponding bracket, right? All right, but we already normalized this to 1, or we already chose normalized base vector. So this is equal to 1. So let it be there. What's the second term? We combine this term with this term. Again, I write the numbers separately. This bracket is a number, as I said before. So this is alpha sz plus sz minus alpha. All right. And then there's the bracket of sz plus, bra sz plus with ket sz minus. Okay. But since these are orthogonal states, we said that the base vectors are orthogonal. This is equal to 0. So this term just vanishes. Okay. Similarly, we can find the other two terms. If we combine these two, again you will get 0 because of the orthogonality. And if you combine these two, this combination will become 1. right? Because we are using normalized base vectors, right? And this simply becomes, we get a contribution from here, bracket alpha sz plus bracket sz plus alpha comes from here, okay, and alpha sz minus that comes from here, bracket of alpha with sz minus, and bracket of sz minus with alpha. What is this? This is simply our inner product of alpha with itself. We said that this was associated with the norm. We said that we needed to be, we said that this is real and positive. Okay, we said that this is real and positive, all right? Actually, we demanded, we postulated that the inner product of a vector with itself is real and positive, all right? Now, if you want this to be real, for example, if you want this to be equal to 1, if you want this to be equal to 1, or if you want this to be real, then each of this has to be real, right? Each of this has to be real. How do we ensure that each of this is real? Okay, there's one way to do that. If bracket of alpha sz plus, all right, if bracket alpha sz plus is the complex conjugate of bracket sz plus alpha, then this is real, because you are multiplying a number with its complex conjugate and you always get a real number, right? Because if z is equal to a plus ib and z star is equal to a minus ib, then z star is equal to a square plus b square, which is real, right? So we see that this can be real, all right? We said, so for probability interpretation reasons, we need this to be real and positive, and we can ensure that this combination is real and positive if this one is the complex conjugate of this and this one is the complex conjugate of this, all right? If these are complex conjugates of each other, then this is real. Similarly, we see that in these two terms, the order has simply changed, all right? So if this is the complex conjugate of this and vice versa, then this is also real, all right? Now, the rule that we already used, bracket alpha beta is equal to beta alpha star, okay? This rule, this postulate ensures that each of the terms in the above equation are real and positive, all right? So if this is true, then this term is real and positive. This term is also real and positive, right? Now, so you see that this rule is important. Okay, you should never forget this. This rule is important if you want to choose bracket of alpha with itself equal to 1. So if you need to normalize the state, all right, if you need to normalize the state, this rule is important, right? So this is very important in quantum mechanics, right? Okay. So this, you could write this, if you remember this we defined as, this was defined as C1, right? The component of alpha on sz plus was C1, this was C1. So if this is C1, then this has to be C1 star, all right? And this was C2, and then this has to be C2 star by this rule, right? So what we have here is actually modulus of C1 square plus modulus of C2 square, all right? Modulus of C1 square stands for C1 star C1, and modulus of C2 square stands for C2 star C2, okay? All right. So I repeat here, sz plus alpha, okay, bracket sz plus alpha is equal to bracket alpha sz plus star, all right? So we have sz plus alpha bracket sz plus alpha bracket alpha sz plus can be written as bracket sz plus alpha multiplied by bracket sz plus alpha star. Okay, remember that a bracket is a number, it's a complex number in general, all right? It could be a real number, but you could think of real number as a special case of a complex number with imaginary part 0. So I'll simply say complex number. So this is a complex number in general, all right? So what we have here is modulus of whatever this complex number is, and this complex number we had already defined as C1, so this is simply modulus of C1 square, all right? So in this case, the condition that bracket of alpha with itself equal to 1, right? You can write this as alpha get alpha bra alpha get alpha is equal to 1, or we wrote this, okay, we found this bracket of alpha with itself, and we found that it was equal to bra alpha sz plus multiplied by sz plus alpha plus bra alpha get sz minus multiplied by bra sz minus get alpha. Okay, now we already had this. This is simply the component of alpha along sz plus direction. You had already called this as C1 and this as C2. So this, using the other rule, this using the rule that alpha beta is equal to beta alpha star, we know that this is C1 star, and we know that this thing is C2 star. Okay, so this condition that bracket of alpha with itself equal to 1 becomes C1 star C1 plus C2 star C2 equal to 1, or modulus of C1 square plus modulus of C2 square equal to 1. Alright, now we already said that the probability, okay, we already said that these expansion coefficients are related, or we said that these are proportional to, or let's say the probability. This is one of the postulates. Okay, the probability for measuring plus h cross by 2 is proportional to, let's say, let me write it like this. Okay, probability for probability for measuring plus h cross by 2 was proportional to modulus of C1 square. We said that probability for measuring minus h cross by 2 is proportional to modulus of C2 square. All right. Now this proportionality could be made into an equality, right? If it's proportional, we know how to make it into an equality, right? But if we see that if you normalize the state beforehand, right? If you normalize the state alpha beforehand, okay, which means that the scalar product with itself, the inner product with itself equal to 1. In that case, you have got modulus of C1 square plus modulus of C2 square equal to 1. Okay, so we see basically that if this is the case, if the state is normalized, this proportionality becomes equality. Proportionality becomes an equality. Why? Because if these are the probabilities for two possibilities, the total probabilities has to be equal to 1. Right? If you have a number of possible cases, if you add the probabilities for each of these, you should get 1. Right? 1 is the maximum probability. Right? For example, if you are tossing a coin, you'll get either head or tail. Okay, the probability for the probability for getting heads is 50% or 1 by 2. The probability for getting tail is also 1 by 2. The total probability of all the possibilities should be equal to 1. Right? If you add up the probabilities of all the possibilities, you should get 1. Right? So we see that if you choose alpha as a normalized state, or if you choose a normalized state, if alpha is normalized, then this proportionality that we postulated earlier can be made into an equality. Right? We get the probability of each possibility. If you add them, you have to get 1. Otherwise, it's not a probability. Right? So this means that you are sure to get either plus h cross by 2 or minus h cross by 2. You could ask the question, what's the probability for getting plus h cross by 2 or minus h cross by 2? Okay, the question is, what's the probability? The question is not what's the probability for getting plus h cross by 2. I'm asking, what's the probability for getting plus h cross by 2 or minus h cross by 2? Okay, so the question is, what's the probability for getting this or this? The probability has to be 1 because we are sure to get either this or this. Right? So that's so if it's probability, all right, if these are probabilities, they have to add up to 1. Right? Otherwise, we'll have to normalize them. If this is the case, we say that ket alpha is a normalized state. If alpha is normalized, then modulus C1 square is equal to the probability of obtaining plus h cross by 2 on measurement of spin component along the z-axis. Right? Similarly, modulus of C2 square is equal to the probability for measuring minus h cross by 2 for the z component of spin in the state ket alpha. Right? So we see that the condition, because earlier I claimed that the condition ket alpha bracket alpha beta is equal to bracket beta alpha star is important. All right. Here we see why it is important, because of this probability interpretation. All right. Now without this rule, right? Without this rule, we couldn't have a probability interpretation, because we have used this rule to make sure that we can indeed have bracket of alpha with itself equal to 1. Right. Without this rule, we cannot have this equal to 1. All right. With this rule, we make sure that this is at least real and positive. Right? And then you can divide it by the real and positive number and then normalize it. All right. So let me summarize what I have said here. We have defined a dual space called the Brass space, and the important application of the Brass space is to form inner products. So we can take a vector, we can take a dual vector, combine them to form a number. Right? So this combination is called an inner product, or equivalently we call it a bracket. All right. So we can take a bra and a ket and form a bracket, which is another name for an inner product. All right. And we looked at some of the rules, and we said that these rules are important for quantum mechanics. All right. And then we talked about states like this: alpha is equal to C1 is Z plus C2 is Z minus, right? And we said that C modulus of C1 square is, we can say, the probability for measuring plus h cross by 2 is proportional to modulus of C1 square. Similarly, probability for measuring minus h cross by 2 is proportional to modulus of C2 square. All right. And in the example, what we saw is that if bracket of alpha with itself is equal to 1, or if this state is normalized, then this proportionality becomes an equality, which means that probability for getting plus h cross by 2 is equal to modulus of C1 square, and probability for getting minus h cross by 2 is equal to modulus of C2 square. All right. So so we get this nice expression. The condition, or the what is demanding that bracket of alpha with itself equal to 1 is the same as demanding that the sum of the probabilities for all the possibilities, okay, probability for the sum of the probabilities of all possibilities add up to 1. This is a basic thing that you might have studied when you discussed probability. Okay. All right. So we have learned to define inner products, and these inner products are important in calculating probabilities of outcomes. Okay. And we have also given rules like this to make sure that the probability interpretation will indeed work. Right? Okay, so that example, you see, I don't expect you to completely understand everything in this example. Right? So we are just building the theory. And don't worry if you haven't understood everything in the example, right? So what you need to do is that you have to understand what we mean by a dual space. What I want you to take home from this class is you have to understand what's a dual space and how we form inner product. Okay, you also need to understand the basic rules. All right, rules like this. All right, the condition that bracket alpha beta is equal to beta alpha star. All right, you could take this as definitions of the inner product. All right, you could take this as definitions of the inner product. All right, now if you understand so much, if you are able to use all these definitions, then it's well and good. All right, after discussing this, we also discussed an example to make these things a little bit more concrete. But the things that we discussed in the example will be looking at in more detail as we go on to the next sessions. Okay, so don't worry if you didn't understand the example completely. Try to follow it. If you don't understand it completely, it's fine. All right, we'll be returning to these concepts again and again.